Today we're going to be talking about the calculus of vector-valued functions. It's coming from sections 13.1 and 13.2 in our book. And it's pretty cool. We're actually getting into vector calculus. So our learning goals for today. We're going to discuss what is a vector-valued function? Why is it a function? We're going to work on using the skills of translating between the equation of a vector-valued function and the graph of a vector-valued function. So if you're given an equation, you need to come up with a graph, or if you're given a set of simple graphs, you should be able to come up with an equation. We're also going to look at parametrizing the intersection of surfaces, which relates to coming up with vector-valued functions. We're also going to look at derivatives and integrals of vector-valued functions. So at the end of this video, you should be able to compute the derivative of a vector-valued function. You should interpret that derivative in terms of the geometry, looking at the tangent vector. We're also going to integrate vector-valued functions, and we're going to use this differentiation and integration and apply it to calculating position, velocity, and acceleration vectors. A particle in space. Let's say that a particle in space has position at time t given by a point in space, and we're going to call it x of t, y of t, z of t. So this is demonstrating the fact that the first component of the position of this particle changes with respect to time. So the x value will change as time changes, the y value will change as time changes, and the z value will change as time changes. Typically, when we represent a vector-valued function, we write it as r of t is equal to a vector where the first component function is x of t, the second component function is y of t, and the third component function is z of t. So, for example, we could look at a vector-valued function that has a vector output that's just in one-dimensional space. Maybe this is a boring example, but I think that it'll help to build up the analog of 2- and 3-dimensional space. So if I look at a one-dimensional example, we could see, let's say that r of t was just equal to the one component vector given by the cosine of t. Now typically we put a domain on t, that t could be any real number, it could be just real numbers between 0 and 2 pi. So in this case, I'm going to restrict t to be between 0 and 2 pi. So what does this function do? As I give a t as an input, I get a one-component vector as an output, in this case represented on the real number line. And my first component, when t equals 0, I get the cosine of 0, which is 1. I'll write that in blue. So here is my vector with my tail at 0 and my tip at 1. And the blue vector is representing when t is equal to 0. Although as t shifts, I could continue to plot points to understand what this set of vectors look like. So as my t value changes, my output, my vector, will change as well. And we just saw that when t was equal to 0, the cosine of t is exactly equal to 1, and so I get a one-component vector. When my t is equal to, let's say, pi over 4, my output is then going to be square root of 2 over 2 as a vector. And I can continue on to see that as my t value increases to pi over 2, I get an output of 0. When my t increases all the way to pi, I get an output of the vector -1. And as I continue forward, I see that by the time I get to a t value of 2 pi, at the end of this domain for t, I go back to 1. So my outputs, in this case, are a collection of vectors that have initials at 0 and terminals somewhere between 1 and -1. So that's my one-dimensional example of a vector-valued function. Let's compare that to a two-dimensional example. So we're going to expand this example 2 dimensions. Instead of just having a function r of t equal to cosine of t, I'm going to have 2 components, and they're going to be both cosine of t for my x component function and sine of t for my y component function. Let's see how this affects the vectors that we get as our outputs. I'm just going to add to the list that we've already begun. So when my t value is 0, my cosine of t is equal to 1. I'm going to eliminate these vector brackets. I think it's confusing when you're looking at the two-dimensional case. There's no need for that. So when my t value is 0, my x component function given by cosine of t ends up being 1, and my y component function given by sine of t, the sine of 0 is 0, which means that when t equals 0, I'm given a single vector, and this single vector has components 1, 0. So my output at t equals 0, I'll represent as the vector where my x component is 1 and my y component is 0. And this is where t is equal to 0. As my t value changes, the vector changes. So for a different t input, let's say that t equals pi over 4, my x component is going to be square root 2 over 2. And my y component is also square root 2 over 2, because the sine of pi over 4 is square root 2 over 2. That gives me a new vector pointing this way, given by square root 2 over 2, comma square root 2 over 2. And that's my vector when t is equal to pi over 4. I continue in this way. I see that at pi over 2, my y component is going to be 1, and I end up with the vector 0, 1. As t progresses along all the way to negative pi, my sine component, the sine of pi is going to be 0. I end up with a vector of -1, 0, and so forth. And we see that if I look at the tips of all of these vectors, if I think of the tip of the vector as the position of the particle at time t, we see that this particle would trace out a circular path in the xy plane. I should have labeled these as x's and y's for my two-dimensional component function. So finally, we just talked about one dimension and 2 dimensions. This is multivariable calculus, and we end up dealing mostly in 3-dimensional space. So what happens to this example when I shift it to 3-dimensional space? I'm going to look at, whoops, I didn't want to erase that. I will rewrite it very quickly. So we're going to look at a new function. Instead of being a function that's cosine t, sine t, I'm going to have my x component function stay the same, my y component function, and I'm going to add a z component function of just t. And in this case, instead of limiting myself to ending at pi over 2, I'm just going to have my t's go off to infinity. My t's are just going to start at 0 and get bigger. What does this graph look like? Again, because I'm trying to map 3-dimensional space onto this flat chalkboard, dry erase board, some kind of board, things will get a little smushed. Let's plot points again. And this is our standard technique when dealing with new vector-valued functions that we don't really know what these vector-valued functions look like. I'm going to plot some points. So for my t value of 0, we have our x component function, our y component function, our z component function in this case is just t. And so that means that it's really easy to know what our z values are going to be in each of these cases. It exactly matches what our input for our t values are. And again, note, maybe I should finish this chart, 0, 1, 0, sorry. The cosine of 2 pi is 1, the sine of 2 pi is 0, and t at this point is exactly equal to 2 pi. So reading across, at time 0, I'm given one single vector. It's the vector 1, 0, 0. So I'm going to add that to my picture. I'm moving 1 in the x direction and 0 in the y and the z direction. This is my time equals 0 vector. As time increases, my x value shrinks a little bit, my y value grows a little bit. I'm circling out the same circle that I circled before in the xy plane, only this time my z value grows a little bit. So I'm going to, at t equals pi over 4, I will have grown a little bit as my vector is cycling this way. So this vector is pointing upwards out of the board a little bit. This is at t equals pi over 4. By the time I get to pi over 2, my t value has grown to be pi over 2 high. And the path that the tips of these vectors traces out ends up being a circular path in the xy plane and an ever-increasing path in the z-plane. You can think of this sort of as the tips of the edges of a spiral staircase. And there's a special name for this type of curve. This is called a helix. Notice that we need not have cosine of t as the x component and sine of t as the y component. We can have it spiral off in other sorts of directions by moving where these cosines t's would be. You can also add coefficients. It would still be a helix as long as it maintains a circular path in one direction and an increasing linear path in the other direction. So another example of a vector-valued function, let's say that we have a function, oops, I use black, r of t is equal to 3t, 2 plus t, 1 minus t. I want to point out that this is something that should look familiar to you. Before we had cosines and sines for our vector-valued function. Now we're looking at a vector-valued function that has linear components. Namely, my x is exactly equal to 3t, my y is exactly equal to 2 plus t, and my z is equal to 1 minus t. These are all linear functions because the t's aren't squared, they aren't cubed, they're exactly degree 1 linear functions. And this is a vector representation of a line, just like we saw before. So this is a line like we saw in a previous lesson, where our direction vector is the coefficients on our t values. So in this case, our direction vector is given by the coefficients on the t's, which is 3, 1, negative 1, and our initial position we could call it our initial position vector, is going to be where t equals 0. So when t is 0, we see that we get 0, 2, 1. I just want to bring this up to mention the fact that we've already seen some vector-valued functions before in the terms of linear functions. Finally, let's say that we aren't given the equation. Let's say that we're just given a pictorial representation of a vector-valued function. This is going to be a complicated one. I'm going to have, this is my x, my y, and my z. And I'm going to say that we have a graph that looks something like this. So this is a graph where it is a parabola that's exactly flat, parallel to the zy plane, where my x is constantly equal to 1. You would need this information to be able to come up with an equation. And this relationship, this parabolic relationship, is just going to be the parabola given by z equals y squared. So I have this parabola in 3 space where my x value is always equal to 1 and my z values are equal to y squared. I want to come up with a vector valued function to represent this. I'll do the easy part